In this lecture, we're going to look at version control or revision control, and also briefly at issue tracking. What then is version control? It's a way of managing a code inventory or a set of code that you've written. It allows you to answer questions such as, when did I introduce a particular bug? And it also, very importantly, allows you to undo mistakes by going back to earlier versions of code. Secondly, using a version control system allows you to work easily with other programmers. So it allows you to merge your work with somebody else's if you've both been working on the same file. And the issue tracking section, which we're not going to talk about very much, but it's something that comes free with the particular revision control system that we're going to look at, called Git and GitHub. The issue tracking allows you to track what bugs have been identified either by yourselves or by your users, and then decide which is the most important bug to fix next. What then is version control? We're going to start off looking at the sort of solo version, so just working by yourself. And there are some of the older version control systems such as RCS, which just stood for Revision Control System, which only allow working by yourself really. They don't do anything clever to allow you to work with other people. All the modern ones, like Git that we're going to concentrate on, allow you to collaborate with other users. So the idea, quite simply, in the solo version, and this may be how you end up using Git yourself, is that you do some programming and then you run your version control system and you commit those changes. You do some more programming, maybe you commit again and you carry on programming. At some stage you realize you've made some mistake, and at that stage you can roll back to an earlier version to undo the mistake. This means that you don't have to worry about keeping lots of old versions of programs, a version 1, a version 2, version 3. Everything is managed centrally within this version control system for you. If you're working in a team, as we have set up here, in a very simple system, Sue creates some code, she then commits it. Meanwhile, Jim is waiting, not doing anything. He then joins the team and checks out what code has been committed to the system already. He then does some programming and commits his changes into the system. At this stage, Sue then does an update here and obtains the updated version of the code. At this stage, Jim is carrying on with some programming and Sue's doing some programming as well. Jim has done a commit and committed the changes that he's made to the central system. But at this stage, Sue tries to commit and no, she can't, because the central system has changed. So she does an update and a merge, and that pulls in the differences that she's made with the differences that Jim has made. And then she commits. Meanwhile, Jim has been doing some more programming, and at the end he tries to commit and is stuck again because the central system has changed. He needs to do an update and a merge. The typical way that this is done is using some sort of centralized version control system. So in a centralized system, there is one linear history of all the changes that have been made on the server or repository, and each revision has a unique identifier. You simply have a working copy of this, and when you do an update, you update your working copy to match the state of the central repository. When you commit your changes, those go to the central repository. And if someone else has changed it, you have to resolve the conflicts by doing this update and merge between your changes and the repository, and then you commit. So that's just what we've seen. If we use a centralized version control system and there's only one programmer working on it, then this kind of workflow shows you what happens. The server has a version of the code, version 1 of the code. We check it out. Jim does some work on it and does a commit. So we have version 2 on the server, then does some more work, does a commit, and we have version 3 on the server, and so on. If we have a team of people, so Jim and Sue working on the code, and there are no conflicts because each one has done an update before they've done any work and nobody's working at the same time, then the workflow is equally simple. So we start off here with the server, has version 1 on it. Jim checks that out and Sue checks it out as well. Jim does some work, commits it back in, and before Sue starts to do any work, she remembers to do an update and then commits it back in, and so on. If, on the other hand, Jim and Sue weren't quite so good at staggering their work and instead did some work at the same time, then this is the sort of thing that happens. So we got to version 3 on the server. Jim updates so that he's got the latest code, as does Sue. Jim does some work, as does Sue. Jim commits his, and version 4 is now on the server. Sue tries to commit her changes, but this fails now because the version on the server has changed. So she does an update, resolves any conflicts by doing a merge of some sort, and then commits her changes back to the server. So we now have version 5 on the server. What I've described so far is what's known as a centralized version control system. So some server somewhere contains the central repository, and this is effectively a remote version of your code. Your computer has a local copy that you work on. To switch back to an older version or to do a check-in of the changes that you've made, you need access to a network. Maybe the internet if the centralized version is somewhere remote, or at least access to a local server where you're storing this work. Examples of this include CVS and Subversion, also known as SVN. On the other hand, a distributed version control system is a system where every user has a version of the full history of all changes that have been made to the code. Users can synchronize their history with each other. They have a central master copy if policy decides to do so. And in fact, most groups do this. It's not absolutely necessary, but generally we have a single master server where that master copy lives, but still every individual machine has a full history of the changes. That means that if you're working on your laptop on the train or something, you can still check out an earlier version, go back to earlier versions and make changes if you realize you've made a mistake. That is the sort of thing you can't do with a centralized version control system. And there are a number of examples of systems that take this approach, including Git, Mercurial, also known as HG, and Bazaar, also known as BZR. We're going to concentrate on Git, which was actually written by Linus Torvalds for use with the Linux kernel. And it's probably the most popular of the systems. In this slide, I show you the basic commands that you need to understand how to use a distributed version control system. I said for the last slide that typically people do have some sort of master copy and master server, and that's in the case of GitHub, in the case of the Git revision control system, generally it's GitHub, which is a server provided by the GitHub developers or Git developers, and that server is free for you to use, providing the work you're doing is open source, but it's also free for you to use if you're a student or an academic. So to download a copy of a piece of code from GitHub and maintain it in a version control system locally, we do git clone git@github.com : then the username where the data are stored on GitHub. In this case, my example is UCL, then a slash, and then something like mycode.git, whatever your project is called, .git. As you make changes, all you need to do is git commit -a. That will commit all your changes, but it will only commit them to your local repository. To put them back onto the main central server, you do git push. Similarly, if somebody else has made changes and you want to make sure you've got those changes locally, all you need to do, you don't need to clone again, you just say git pull. Git status tells you where you're at in terms of having made changes but not committed them, or committed changes but not pushed them back to the central server. And git diff allows you to look at differences between different versions of the code. Those are the basic commands that you need, and most of the time, probably 90% or even 95% of the time, those are the only commands you need. What's actually going on with all this is a little bit more complicated than that, and there are some commands that we can give that actually we can sort of sidestep. So this is a little bit of information about how things kind of work underneath those very simple commands that I've just introduced. In your working directory where you're working on your code, if you create a new file that you want to add to your Git repository, you have to say that you want to add it, and you do that with git add. Then goes into what's known as a staging area, and to actually commit it to your local repository, you do git commit. Now I can also do git commit -a, and that won't add new files that you've created, but it will do the adding and committing which is necessary for files that you have simply modified. So if you add a new file, you need to use the git add. If you modify a file, just do git commit -a. That will get it into your local copy of the repository. When you do git push, it will go onto the remote repository. Git fetch will pull down a modified file to the local repository, and git checkout will then get the code actually so you can use. Again, you can replace git fetch and git checkout with git pull. That will do both of those steps in one. And git merge is another command that you need, which allows you to merge your updated local repository with what you're actually working on. So if two people have changed a file, you've changed it locally, somebody else has changed it. When you when you want to deal with this, you do a git fetch followed by a git merge. If you do a git pull, then it does the fetch stage automatically without the checkout stage, and you then do the git merge to sort things out. In fact, Git is very clever. If it can do the merge when you do a git pull, if it can do the merge automatically, then it will. It'll just do everything for you. It's only where two people have actually changed the same bit of the code that you really need to worry and make the changes yourself. And it will guide you where those changes are. The next useful feature of a good version control system is the idea of branches. So generally what we have is a master branch. So everything I've talked about so far uses the idea of a master branch. We simply work our way along making commits. Each commit is indicated by one of these little red balls. But often, particularly if we're working with other people, it's a really good idea to be able to create a separate branch for a new feature that you want to develop. So what we do is we create a new branch here. I'm working on this and adding new code to it. I might also decide to branch off a second time from this and add some more code to that, something maybe a bit more experimental. And I've decided, okay, this one now I'm happy with. I can merge that back into the master. Meanwhile, somebody else perhaps has been working on some bug fixes, and all those then get merged together. In this example, perhaps we've given up on this. Perhaps that was something we tried and it didn't work. So we just leave it and we can delete this branch if we wish. In Git, if we type the command git branch, it'll tell us that we're on the master branch. If we want to create a new branch, we say git checkout -b and then the name of the new branch. And again, if we type git branch, we'll see that we've got the master branch, but the active branch, which is indicated with a star, is this new branch called experiment. If we wish to share our new branch that we've created with other people, and we want to push it onto the central master copy of the repository, we can do that using git push origin experiment, where experiment is the name of the branch that we've created. Now, that's a bit of a mouthful. It's a bit of a pain to remember this every time rather than just doing git push. So if we do git push -u origin and the branch name, then it will remember that we want our branch to be synchronized with origin. And origin is just a nickname for that main central server, the master repository server. So once we've done that, all we have to do is git push, as we did when we were sitting on the main branch. If we want to get a new branch that somebody has put on the server, we can say git checkout origin / and the branch name. Once we've got it locally, we can just work with it in the normal way. Another thing we want to be able to do is merge branches. So I showed that in the diagram. So if we've developed a branch called experiment and we want to merge it into the central master branch, then we check out the master branch, which you do with git checkout master, and then we simply say git merge experiment, where experiment is the name of that experimental branch. That will take all the changes that have been done in this experiment branch and merge them into our master branch. And in fact, merging other people's work is done in exactly the same sort of way. Once we've finished with the branch, we want to get rid of it because we've merged it in or we've decided that it's no good, then we can do git branch -d and the branch name. Now that will delete the local copy, but it won't delete the remote copy. So to do that, we have to say git push -- delete experiment, where experiment is the name of the branch. You should have a development branch and a stable branch. So obviously when you're starting to develop a piece of code, you don't need this. But once you've got to the stage of having released the code to somebody else, you have that stable branch. And usually people make the master the stable branch. Then the only changes that happen directly on that branch will be simple bug fixes. Every new feature you develop has its own development branch, gets merged back into the central branch, and then gets deleted. So you should create temporary branches for experimental changes, and if you release code to others, you can choose to make what you call a release branch, or you can keep the master branch as your set of release branches. That's my preference. I like to make the master branch where all the released versions go. This then indicates a kind of timeline of what people do. This is just one way of doing things. This has a separate release branch here. My preference, as I said, is to keep all the releases on the master. So here we've started with this position. Somebody has done some development on this development branch. Here they've forked off to create particular features. That's been merged back in here. Somebody did a bug fix on the master branch here, on a hot fix branch, and then merged that back into the master. Those hot fixes have also been merged into the development branch at this stage. So those changes that have been made in the feature branch, when they're merged back into the development branch, they're going to pick up those hot fixes as well. At this stage, we maybe decide this is good enough that it's close to a release. So we do some debugging. I tend to call this a candidate branch rather than a release branch. And then it's decided, no, we need to do a bit more work on here, maybe make a little more change here, add another feature here. But at this stage, we've decided this one's good enough. We're going to release that to the rest of the world. So that goes back into the master. Here, somebody else has been developing gradual features, maybe, a big feature that needed a lot of work. From this earlier development version. This then gets merged in here. These changes get merged in. This all goes back now into the release branch as a candidate version, and then back onto the master branch, ready for release to the outside world. Then somebody picks up this version and starts to do some more development, and so on. So you can see this kind of network of changes can become quite complicated, but in reality, particularly if you're working by yourself, it's generally very much more simple than that. Now, Git labels each commit with what's known as an MD5 checksum. Now, this is quite a long, complicated set of letters and numbers. It appears like a random string of letters and numbers. And this gives a unique label to each commit. However, these, of course, are very difficult to remember. They're 20, 30 characters long. Usually the first 5 or 6 characters are unique to what you're doing. So you only need the first 5 or 6, but it's still very long and difficult to remember. So you can create tags instead, which, label working versions. So certainly everything that's on your master branch that you release to other people, every version on there should have a tag associated with it, which will typically be something like version 1.0 or something like that. And you should only do your real science with specific tagged versions and make a note of which one. That allows your science to be reproducible because you can go back to exactly the version of the code that you used to produce a certain set of results. Some journals are actually requiring now that you produce, if you use code or you write code that's part of your, part of what you publish, then you make that available on GitHub and you specify exactly which version of the code was used. And some journals even make clones of your repository at the time that it was developed. So F1000 does that, for example. Here then are some simple examples of how you do tags. We can say git tag v1.3 to tag the current last commit. That will just create a very simple tag for you. If you want to tag another commit, then you just say git tag your tag that you want to use, and the MD5 checksum, in this case just the first 6 characters of it, of a previous commit. Once you want to push these tags onto the central repository or the master repository, you do git push --tags, and that will push all of the tags to the origin. which, as I said, origin is an abbreviation for the central master repository. GitHub is a website which will provide this master repository role for you. You don't have to use GitHub, but it's very convenient. And if you're working in a team, it takes away any complications of having to connect your computers to each other in order to share code. It works, in effect, as a master repository for you. This is a slightly old version of one of the slides or pictures from the GitHub website. But if you go to github.com, you'll find instructions there on how to set up Git, how to get started, how to create a repository, how to fork a repository. So this is something that allows you to copy somebody else's repository where you don't have permission to write to it. But you can create a local copy, you can work on it, and then you can create what's known as a pull request, which allows them to know that you've made some changes that you suggest they integrate into their project. And you can also use it as a sort of social media type system where you can create a local profile for yourself, you can follow friends, you can watch projects and so on. In order to do all this and make it simple to do, you need to make use of SSH keys. Now, I'm not going to explain how to do this here. This is all described in the exercise that you can download. So there's quite a long tutorial that you can download, work through all these things, and this first stage of setting up SSH keys is described in some detail there. But once you've done that, you've created your keys locally, so you create what's called a private key and a public key. The public key you can share with other people, and when you want to encrypt a piece of data or a file, you use your private key and their public key. Then they can decrypt it using your public key and their private key. Now, this public key, private key system is the sort of thing that when you see HTTPS or a little shield in the top left-hand corner of your web browser, it's making use of this sort of thing to encrypt data. And this is really a very high security system, which all sort of internet banking, internet transactions involving shopping and so on, all rely on this sort of system. But as well as being useful for encrypting data and sending it, it is also useful for identifying you as an individual. So by sharing your public key, you can identify yourself when you log on using things like SSH, so you don't have to provide a password. And this is what you're doing here. So again, if you follow the tutorials, it will explain how you do this on GitHub, but essentially by pasting your public key into a box on GitHub, it will allow you then to do all these pushes and pulls and so on without having to provide a username and password on the remote machine. To create a repository, it's very simple. You just go to your GitHub page and you type in a repository name. You may be a member of different groups. In your case, you won't be unless you've set something up like that previously. But basically, you just add a repository name. You can add a description, and you click public, which means that anybody can see the repository, but you can still control who can push to it. If you want a private repository, you either have to pay or you have to have set your account up as being a student account or as being a member of academic staff at a university. You can also choose, when you create the repository, to initialize the repository with a README file, and that just allows you to have some file that's in there to get you started effectively. And you can also add what's called a git ignore file. Now, that's not particularly important for things like Python, but it for compiled languages, for things like C and C++, it allows you to specify files that you don't want to be synchronized with GitHub. Now, you can choose individually which files you want to synchronize anyway, but if you added a whole batch of files, it would automatically ignore these particular files. So if you're using a compiled language like C, you have intermediate.o files, object files, and you don't want those to end up on the repository. You also probably don't want your executable program to end up on the repository, so you can add that to your git ignore file. But you'll find there are git ignore files, default ones set up for different languages, and there will be one for Python, and that will stop it from putting the PYC files, the part compiled files, onto the server. In conclusion then, Git and GitHub provide you with tools that can make your development easier, safer, more reliable, more correct, and more collaborative. The tools can be complicated and they take some time to learn, but as I said, that small number of commands, git clone, git pull, git push, git branch, git add, and git merge, really do 95, probably more % of things that you ever want to do. Occasionally, of course, you want to check out an earlier version. You want to roll back to an earlier version. That can be useful, but the number of times you actually need to do that tends to be very, very small. Again, I have provided for you this self-paced learning activities and tutorial, which I highly recommend you work your way through. Using Git and GitHub for your project work really will make everything much simpler for you. You will create yourself essentially Python modules for the different layers that we've talked about, and you can then share those between you. So each person could be working independently. The person who's working on the business logic module can update it, do what they like with it, push it into that central server, and then other people can just do a git pull and they'll get the latest version of the code without people having to tell them that I've made some changes, I've added new stuff, and so on. The website for Biocomputing II provides a number of links to different places. There are a couple more books, online books here. There's one on Git here. There's another one on SVN, which is another revision control system. But really, at the moment, Git is probably the most popular one. So that's the one that I would encourage you to use.